Hello, and welcome to the module Basic Lab Equipment. In this module, we'll be going over some of the basic lab equipment we use to measure signals and generate signals. One of the most common devices we'll use is a multimeter. We use multimeters to measure constant quantities, so these are DC currents, voltages, and resistances, as well as AC currents and voltages, as long as the AC amplitude is not changing. Make sure to measure voltages in parallel and currents in series. This is because a multimeter in voltage measurement mode looks like an open circuit, while a multimeter in current measurement mode looks like a short circuit. Make sure to measure resistances out of circuit. That means to completely remove the resistive element you want to measure from any other connections before connecting it to your multimeter. The multimeter has a number of different terminals on the right side over here. You need to make sure that you're on the correct terminal corresponding to the function you've selected. For example, if we wanted to measure a voltage, we'd select DC voltage measurement over here, and we'd use this low terminal here as well as high terminal, as that's the one which has a voltage measure there. If we want a DC current, we'd select DC current, which is right above DC voltage, so hit shift and then DC current. Again, use the same low terminal, but this time use the terminal measured with an I for the high side terminal. For example, if we wanted to measure the voltage across our resistor, we would select DC voltage and then connect the high port to our voltage high and the low port to our voltage low. We do the same thing with current, but we would select current measurement on our multimeter. We would connect one terminal to our current high and the other terminal to our current low. Same thing for resistance. When we need to measure time varying quantities or signals that change rapidly, we'll use an oscilloscope. The oscilloscopes you'll be using have a number of different channels. They have 4 channels seen here by the 4 different colors. Each channel has its own vertical processing unit, and this will let you adjust the offset or the amplitude of the signal that you're looking at. In addition, all channels share the same horizontal processing unit, which lets you shift the waveform left and right in time, as well as change the time scale that you're looking at. If we look at the front panel of our oscilloscope a little closer, you'll see that each channel has a stack of knobs and buttons above it, which will adjust the vertical parameters for that channel. So you can adjust the vertical offset as well as the vertical scale. All channels share the same horizontal controls, which allow you to shift the waveform left and right, as well as zoom in and out in time. One of the more useful buttons is the measurement button here, which will give you a bunch of different options for measuring signal amplitude, frequency, offset, and a lot of the common measurements you're trying to make. There's also a set of knobs and buttons to adjust the trigger level, which we'll go over a little bit more later. When you're attempting to make a measurement on a signal, make sure to expand it using your vertical controls to fill up as much of the screen as possible. You don't want it going outside of the viewport, but you want it as large as possible. This will give you the best measurement. Once you have a waveform up on the screen, there's a couple of useful pieces of information that the scope will display to you. The first of these is going to be your vertical scale. We see that down in the corner here. So here we have 50 millivolts per division. So these dotted lines are divisions. There's 6 divisions here, and we can tell we have a 300 millivolt signal up on our screen. You'll notice that there's a little tab with the number 1 down here. That lets us know that this is channel 1 that we're looking at, and that tells us where the 0 point of channel 1 is. So this waveform starts from 0 and goes to 300 millivolts. You can adjust the position of that to shift the waveform up and down using the vertical position knob. In the upper corner, it gives us our time base. This lets us know how many seconds per division we have going this direction. So 500 microseconds per division, and we can see we have a period of about 1 millisecond. Additionally, we'll see some information on how we're triggering the signal. And you can see we're triggering on channel 1, we're triggering on a rising edge of channel 1, and we're triggering at 154 millivolts. What that means is your scope is going to find 154 millivolts, which is about there. We have 50 millivolts per division. And it's going to find a rising edge at that voltage, and it's going to try to line that up with the trigger tab seen here. It's going to try and keep this part of the waveform, or this element here, constant in time and always plot it right there. Really the best way to tell how this works is to go play with the scope and see how various trigger options affect how it's displayed. But in general, you want your trigger set to about half the value of your waveform, so somewhere half between the min and the max values. In order to generate waveforms, we use something called a waveform generator, or sometimes a function generator. This will allow us to generate sine waves, square waves, a number of different options. One of the most important things to remember about your waveform generator is that internally it has a series 50 ohm output resistance. What this means is that if we connect this up to another 50 ohm resistor, you'll see we now have a voltage divider here. So if we measured the voltage here, that's going to be affected by the pull down 50 ohm resistance. To deal with that, all waveform generators will have some sort of output impedance selection. You can see it says 50 ohms right here, so this is the waveform generator assuming that it's going to be connected to a 50 ohm load, as we can see over here. And all the amplitudes and offsets that you input will be correct then for a 50 ohm load. If you're not using a 50 ohm load, for example, if you're connecting this directly to an oscilloscope, or maybe to some sort of IC which has a high impedance load, you'll set this up as high Z, or high impedance output, so that your amplitudes and offsets are the same. If you're in a situation where your output waveform is much larger or much smaller than expected, double check you have the correct output impedance. Notice there are two ports on your output of your waveform generator. One of them is labeled output, the other one's labeled sync. The sync port is used for triggering oscilloscopes and will always output a 50% duty cycle square wave, so it's not very useful for generating a signal. Always use the output port. Additionally, we can turn the output on and off with this button, so if you're not seeing anything, make sure that your output's actually turned on. So let's just take a look at an example waveform and see how would we generate that using our waveform generator. We've already determined that this waveform starts at 0 volts and goes up to 300 millivolts, as well as that it has a period of 1 millisecond. So it's a square wave, looks like a square wave, so we'd select square wave on our waveform generator here, and then we would input 300 millivolts for our amplitude. So we already know type is square wave and amplitude is 300 millivolts. We have our frequency as well. It's got a period of 1 millisecond, so the frequency is just going to be 1 over that. Now a waveform generator is always going to try and generate signals with a 0 average value, so it's always going to center your signals around 0. Because we want our signal to be from 0 to 300 millivolts, we're going to have to add an offset. We need to shift that signal up. So adding an offset of 150 millivolts is going to shift this signal up so that it starts at 0 and goes to 300. Now if we wanted to look at the waveform we just generated, we would connect the output port of our generator directly up to our oscilloscope over here. Now because we've connected it directly up to an oscilloscope, we need to make sure to use high Z output mode. So we change this from 50 ohms, we change that to high Z, and that would give us the waveform we see here. If we need to generate DC voltages or currents, we'll use a power supply or a DC voltage source seen here. The ones that we have in the lab have a number of different outputs. The first one is this labeled 6 volts. That'll give you voltages between 0 and 6 volts with some current rating, happens to be 5 amps. So that's adjustable. Remember, the black is the ground, so you'll connect that to the low voltage, and this red is the higher, so that'll give you your positive. And you'll have positive minus between those two, whatever voltage you've set it at. To set that voltage, just select this plus 6 volt button up here. You can use the knob to set it, or you can use the arrow keys if you like. There's also plus minus 20 volt connections here. Now again, ground is this black port. The minus is going to give you the negative voltage of what the plus does. So don't try and connect between minus and plus. That's going to give you twice the voltage you like. Connect between the center, or black, and the positive to get anywhere between 0 and 25 volts. Again, this has some current limit. This is typically 1 amp on this supply. The green port we see here connects back to earth ground. On some of your sources, that'll be shorted to one of these other ground terminals. If it isn't shorted, generally a good idea to just connect that with a jumper. You can turn the output on and off without reducing any of the settings with this button here, which is sometimes useful as well. If you need to limit the current of your voltage source, hit this voltage current button and you can adjust what the limit is. Now those are basic pieces of lab equipment, so let's go over how we might use them. This is an example circuit we used in the previous module. And if you'll remember, we have a pulse input here that goes into some circuit. We have a number of different voltage supplies to supply our rails. Then we have an output over here. To generate this pulse input, we're going to use our function generator. Notice that there's a 50 ohm resistor in series, so everything inside this box is actually modeling our function generator. We put our function generator on high Z output because we're connecting it directly to an IC, and we don't expect very much current to have to flow there, so we're going to use high impedance. So we do that with our function generator. Both of these voltage supplies we can use, or we can generate, with the same piece of equipment. You notice one's at 4 volts and one's at 12 volts. So we'll use the 6 volt output of our power supply or voltage supply for this guy, and we'll use the plus 25 for this guy. And we'll just set those voltages accordingly and give them reasonable current limits. So that takes care of all of our inputs and rails. Now if we wanted to measure the output, we'd use an oscilloscope over here. We do that because it says it's a pulse generator, so we're assuming this is going to be some time varying signal. We want to see how it varies. We don't want to just measure a constant quantity. So we're going to use an oscilloscope for that. Additionally, if we want to measure CV or maybe trigger, maybe discharge, we'd use an oscilloscope for those as well. Now it probably turns out that CV is maybe a constant voltage, maybe not. We don't really know. But if you use an oscilloscope, you'll be able to tell. Then you can change over to a multimeter later if it turns out it is a constant quantity. If we wanted to double check that our voltage rail was at the correct voltage and that it was clean, didn't have a lot of noise on it, we'd use a multimeter for that. So we're using our oscilloscope to measure outputs because we expect them to vary. We're using our multimeter to measure voltage rails because we expect them to be constant. We have our power supply generating both of these sources here, and our function generator set up for our input. So that's the basics of how you use this lab equipment. Most importantly, go into the lab, try and hit some buttons, try and figure out what does what. That's really the best way to learn this equipment.